Hi everyone, welcome back. Today's lesson we're going to be talking about arc length and curvature. Now we are going to use the same definition for arc length that we learned back in Calc 2. And this definition says that assume that r of t is differentiable and that r prime of t is continuous on some interval from a to b. Then the length of the path, r of t, for the parameter t being bounded between a and b is going to be equal to the integral from a to b of the square root of the sum of the squares of each individual component for r of t. Or in other words, it's going to be the integral from a to b for the magnitude of r prime of t. Now, on the left of your screen here, I have a depiction for what it is that we're looking for. The arc length L here is denoted by L, and that's this red curve. And the blue curve behind it is the curve that's being modeled out in R space 3, given by r of t. And we have our two bounds, t is equal to a and t is equal to b. And within those bounds, again, we're trying to find that length of the curve. So in this particular question, we want to determine the length of the curve, which is r of t, given by the components 2t, 3 sine 2t, and then 3 cosine 2t. And this is going to be on the interval from 0 to 2 pi. And so again, the first thing that we want to do is we want to take the derivative for the function that we're given. Taking that derivative, the derivative of 2t is just 2. The derivative of 3 sine 2t, we're going to use the chain rule here, which is going to be 6 sine of 2t. Oops, excuse me. 6 cosine of 2t. There we are. And then taking the derivative of cosine while accounting for the chain rule will then lead us into negative 6 sine of 2t. And once we're able to extract this, then we want to take the magnitude. So we're going to take the magnitude here for r prime of t. That's going to be 2 squared, which is 4. That's also going to be 36 cosine squared 2t plus 36 sine squared 2t. And then we take the square root of all this. And once we're able to get this, then we're going to go ahead and we're going to factor out a 36 from the last two terms, which will leave us with 36 multiplied by cosine squared of 2t plus sine squared of 2t, all a part of our radicand. And once we have this, then we can go ahead and we can say, well, cosine squared of 2t plus sine squared of 2t, that's going to be the Pythagorean identity, which is going to leave us with 1, which means it's 1 times 36, which then just gets us 36 plus 4, which is square root of 40. Now, square root of 40 can simplify into 2 root 10. So what I want to do at this point in time now that I have the magnitude, is I want to find the length of this segment bounded by that parameter for t. So in order for me to do this, I'm going to go from 0 to 2 pi, and I'm going to integrate that magnitude of r prime of t, which in this case was 2 root 10, and I'm going to integrate this with respect to t. So once my integration happens, this is just going to be a constant, so it's going to be a constant multiplied by the distance for that interval, which will be 2 pi times 2 root 10, which will leave us with 4 pi root 10 as the length of the curve that is parametrized by that vector r of t, and that is bounded by the interval from 0 to 2 pi. Okay, so that's pretty nice to see. So the other thing that we then want to see is, could we then find a function that will produce this length for this arc or for this curve that we're going to be looking for. And to answer that question, or to analyze that question, we're going to need a little bit of tools at our disposal here. So I'm going to go ahead and draw this, again, three-dimensional grid, or this three-dimensional axis. Okay, there we are. Okay, perfect. So we're going to have our x-axis, our y-axis, and then we're also going to have our z-axis. And so again, what we want is we want this curve that we're trying to work with here, and we're going to call that just curve C. And once we have curve C here, what I want to do is, again, I want to identify that I will have curve C being parametrized by some vector r of t. So what's going to happen here is that analyzing that vector, so we go here. What I'm going to do is I'm going to call this r of a. And then what I'll do is I'll construct another vector. And this other vector that I'm going to construct is going to be r of t. Okay, here we go. So this is going to be r of t. Now, what's happening here is that I'm choosing my value. My value here is going to be a for my starting point. However, my value for t is going to kind of be a slider. It's not going to be a fixed point like it was before, where I want to stop at some value for b. Instead, what I want to do is I actually want to stop at some value for t, which means we're going to be able to move this vector, or in other words, we're going to be able to move the ending point, or that stopping point, for this particular curve. When we do so, we're going to be sketching out this curve. And this curve, again, it can stop wherever it would like. This curve is going to be some function that has t embedded in it. And the reason for this, again, is because let's say we chose to stop here for this t value. Well, in that sense, we would only get a small portion of the curve, and then we would still be able to calculate that arc length for that specific length of the curve. So identifying that we can have this arc length function actually pays off, because we are able to build a function in terms of t. So when I'm looking for my arc length function, well, finding the arc length is still going to be very similar to what we were doing before, where we're going to have that the arc length is the integral from the starting point, which was a, but now we're going to end at some value for t. All right, so we got that we have to account for. Next, we're also going to be integrating the magnitude of r prime. And notice, if we're choosing t as our stopping value, we can't integrate with respect to t, because then our upper bound will be the same variable that we're trying to integrate with, which means there won't be any stopping points. So there's that one small issue. So instead of using t as my parameter for my function, what I'll do is I'll say this, that c is parametrized by r of u. And in that instance, as soon as we make this substitution here, well then analyzing the part of my length that I need for that arc length, this will now be the magnitude of r prime of u with respect to du. And this is where we want to be, because now we can actually determine what is that arc length function. So in this example that we're going to work here, this is going to say determine the arc length function for r of t, which is the same function that we were working with before, 2t times 3 sine of 2t times 3 cosine of 2t. Okay, so we want, again, this arc length function. And to determine this arc length function, again, what we're going to do is we're going to say we're going to be working with s of t. And s of t, this is going to be my arc length function. This is now going to be integrated from the interval from a to t, so from a to t, with the magnitude of r prime of u. And we're going to have to integrate with respect to u. So the first thing that we then have to do is we have to find this magnitude. So interpreting r of t in terms of r of u, then we still get the exact same function, except this function, again, now is just in terms of u instead of t's. And finding this derivative, well, we already found the derivative from the previous problem. That derivative that we were initially looking at was 6 cosine of 2u, and then negative 6 sine of 2u. Finding that magnitude, so finding this magnitude will result in the same magnitude that we just found, 2 root 10. So inserting all of these values into my arc length function, a, well, we now need to determine this value for a. And what I will do here is I'm going to determine that my a value is going to be 0 because I want to see what's going to happen if I start at t is equal to 0, or in this case, a is equal to 0. So I'm going to just briefly say that I want to use a as being 0. All right, and typically when we start off on exam or a quiz, I will more than likely give you this value that you want to start with. So we start from 0 and we go to t for my integral. My integrand will then be 2 root 10 with respect to du. Integrating here will then leave me with 2 root 10 multiplied by t. And this is my arc length function. Now, why is this my arc length function? Well, this is the arc length function specifically because if I wanted to find the arc length for the value beginning at a and ending at some stopping point t, then I can just make my substitutions in for t and we're done. Look at how that correlates with the first example that we did. That arc length that we found, which was 4 pi root 10, just translates into substituting in the value for 2 pi, in other words, a stopping point, for my arc length function. So 2 root 10 times 2 pi would get me that arc length of 4 pi root 10. So this is really nice, and this turns out to be real interesting because now we can get this arc length function and we can bypass the whole process of repeatedly doing the integration to just establish this function and use this function to determine any arc length that we wish to find. All right, so that's kind of nice. So what I want to do now is I actually want to use this function here, and I'm just going to say this is going to be the arc length function, which I'm just going to call s, and it's going to be s is equal to 2 root 10 times t. Great. Now, what we can do is we can solve for t. So I want to solve for t. Now, if we solve for t, then what's going to happen here is that we're going to be left with t is going to be equal to s divided by 2 root 10. Now remember what s is. S is this arc length function. Which means that if we do this, we now have a representation for t. In other words, that stopping point, that value for t, we now have that stopping point in terms of its arc length function. Okay, so what we can do now is we can now start anticipating. Well, if I started looking at my function, say I had r of t, this function, r of t, is 2t, 3 sine of 2t, times 3 cosine of 2t. All right, we already knew that, so that's great. But check this out. What if I make my substitution, because I know what t is, what if I make this substitution in for my t values? Well, then that becomes way more interesting. Because now, when we have r of arc length divided by 2 root 10, what's going to happen here is that we're going to be left with 2 times this arc length divided by 2 root 10. Component y is going to be 3 sine of 2 multiplied by s divided by 2 root 10. And then the z component will be 3 cosine of 2 multiplied by s over 2 root 10. So check that out. Now, we can do a whole bunch of simplification here, which is going to be really nice. So if we simplify here, the first component, in other words, the x component, will now be left with s divided by root 10. Let's see. So this is s divided by root 10. Second component, that's 3 multiplied by sine of s over root 10. And then the last component is going to be 3 cosine of s divided by root 10. That's really neat. And now I say that this is really neat because we now have this curve that was initially parameterized by some stopping value for t. All right, and remember, that was my arc length function. So we had some curve that was parameterized, and we had a stopping point of t, but now this curve is now determined by the arc length. In other words, if we wanted to now find at what time the object traveling on this curve would have traveled a certain arc length, then we could then say, well, at time t, that object will be here. So not only are we able to find the arc length, but now more specifically, we're able to determine where the object will be at a given time. That way we can intercept that object if possible. So again, this is really beneficial. So let's look at an example now that will implement this specific example. So on this example, we're going to say where on the curve r of t, which is equal to 2t, 3 sine of 2t, and then 3 cosine of 2t, are we after traveling for a distance of pi root 10 over 3. Well, again, in order to answer this question, we need this arc length parametrization. And again, having that arc length parametrization is going to prove very useful for us, as we just saw with this question. And I want to make sure I copy this down. There we are. Whoa. Que pasa? Okay, here we go. So what I want to do now is I want to insert that value for pi root 10 over 3. That's going to be the distance. In other words, that's going to be the arc length that is actually given to us. They're saying, hey, what you found was that that arc length was being traversed by pi root 10 divided by 3. So now we want to find out at what time is that going to, or what position is that going to occur with. So making our substitutions here, so we get pi root 10 over 3 divided by 2 root 10. Making this substitution now, well, s is going to be pi root 10 over 3 divided by root 10. 3 sine of all that again. Pi root 10 divided by 3 divided by root 10. And then finally again, 3 cosine of pi root 10 divided by 3 divided by root 10. We can now simplify this. And when we simplify this, we're now going to be able to get, for the first component, is going to be pi thirds. Second component is going to be 3 multiplied by sine of pi thirds. And the last component will also be 3 multiplied by cosine of pi thirds. Okay, so again, that's looking pretty good now. So all I want to do now is finish evaluating this specific position vector. So sine of pi thirds, well, pi thirds is 60 degrees. So sine of pi thirds is then going to get me root 3 over 2. So this is going to be 3 root 3 divided by 2 for the y component. And then cosine of pi thirds is a half, which means this is going to be 3 halves. So the value that we're looking for, or the point, so we are at the point, ordered triplet here, of pi thirds, 3 root 3 over 2, and then 3 halves. That is the point that we can intercept this object at if we know how much of that curve this object has now traversed. So again, that's now pretty amazing for what we want to see. Now let's keep working with that whole process of the arc length. Well, taking that arc length formula once again, so I'm going to be using s of t, which is going to be equal to the integral from 0 to t multiplied by the magnitude of r prime of u du. As such, remember, this was my arc length formula. Okay, now, if I take this arc length formula, or if I take this arc length, now remember what we did in Calc 1. If you take some random length, whatever that length may be, either kilometers, meters, miles, inches, centimeters, anything like that, as long as we take that length, and when we take that length and divide it by time, or divide it by a small subinterval, then we get a rate. And that rate will then get us a rate of change for this specific object. So what we want to do now is we kind of want to find that arc length, or in this particular case, we want to find the rate of that arc length. So in order to do that, calculus-wise, what I'm going to do is I'm going to apply the derivative onto both sides here. And applying the derivative with respect to t, so I will interpret this for you all, that when, oops, you know what, I wanted this piece here in a different color. There we go. Now, the interpretation here is that we're taking that length, that arc length, and we're identifying the rate of change with respect to time. In other words, what we're going to be looking at is going to be how fast this curve is changing with respect to t, or how fast this arc length is changing with respect to t. In other words, what we're really finding here is the speed of the curve. So what we actually get here on the left-hand side, well, if we just make this ds over dt, that's kind of nice. On the right-hand side, we're going to use the fundamental theorem of calculus, part 1. That's a nice fundamental theorem, which says, hey, if you're taking the if you're taking the derivative of the antiderivative of some integral that ends at a bound of t, then these are going to be inverse operations of one another, and they're going to undo themselves, which means what we should have is the integrand evaluated at that upper bound, which means we're going to be left with our magnitude of r prime of t. And again, this is the speed of the object that's traveling on this curve. Just by analyzing the arc length and then taking the derivative with respect to time, we then have the length for this object, or the arc length of this object divided by time, which again will translate into the speed at time t. So this is what we get for this. And again, that's why we needed that whole arc length formula. So if we want to identify the speed at time t, this is going to be ds over dt, which is equal to the magnitude of r prime of t. Now, that should stand to reason, because we were analyzing this whole process of trying to correlate this position with this velocity, with this acceleration, with this speed, and now we can kind of see that speed kind of is a result of what it is that we were initially looking at. So let's go ahead and let's try to do an example to find a certain speed for an object traveling on a certain curve. So on this example, we want to find the speed at time t is equal to 2 seconds of a particle whose position vector is r of t, which is equal to t cubed in the I component minus e to the power of t in the j component plus 4t in the k component. And we're going to say here where distance is in feet. All right, so again, we want to find this speed. And so in order to find the speed, what we're going to need to do is we're going to find the derivative of this position function, and then we're going to find its magnitude. So taking the derivative, 3t squared in the I component minus e to the power of t in the j component plus 4 in the k component, that's going to be my derivative. Now that I have this, I am going to make my substitution for 2. So what I'm going to do now is find r prime evaluated at 2. Oops, there we go. Which will now leave me with 2 squared. That's going to be 4, so that's going to be 12, because it's multiplied by 3, minus e to the power of 2, and that's in the j component, plus 4 in the k component. And so now I would just want to find the magnitude. All right, so let's go find the magnitude. So the magnitude at 2. Well, that's going to be 12 squared minus e to the power, or sorry, plus this quantity, negative e squared squared. So it's going to be e to the 4th plus 16. And then you're going to go to your calculator, because that's what I'm going to go for. So I'm going to have 12 squared plus e to the power of 4, and then we're going to add 16 to that. And we should get a really big number, large decimal. And then we're going to take the square root of that. And when we take the square root of that, we should get 14.65 approximately. So the speed, oops, double P. So here we go, the speed of the particle at t is equal to 2 seconds is approximately 14.65, and remember, we were given the length units. This is going to be feet per seconds. So 14.65 feet per seconds. Great. Now, let's go ahead and let's start extracting a little bit more items. That way we can keep working with some of these values. So one of the first things that I want to do here is I want to start extracting my unit tangent vector. So we know the unit tangent vector. This unit tangent vector, I'm going to say that the unit tangent vector for r of t, so unit tangent vector, I'm going to say for r of t is going to be t, which is going to be r prime of t divided by its magnitude. Now again, if we're given a vector position, r of t, well then when we take the derivative, then we have a tangent vector. And once we're able to extract that tangent vector, we want to make sure we make it into a unit vector. That way we can get a unit length of 1. Therefore, we're going to identify this as a unit tangent vector. And the unit tangent vector, this is going to be very crucial for what we need. The unit tangent vector, or we could just say the tangent vector, because the unit tangent vector and the tangent vector both have the same direction. So the unit tangent vector indicates the direction of the curve C. So again, now we have this unit tangent vector that's kind of letting us know what way we're going to be traveling along this curve. Okay, so that again is looking pretty good. So what we're going to do now is we're going to start analyzing what the curvature of this function or of this curve is going to be. So what we want to look at is how quickly is the curve changing. Well, in order to identify how quickly this curve is changing, we can take this unit tangent vector, which lets us know the direction in which the curve is traveling, and we can divide it by its arc length. So take that direction that the vector is pointing you in, and then take the arc length and divide it by that arc length. So in order to identify this curvature, so we want to look at the curvature, we're going to say that the curvature curvature of a curve is going to be kappa, which is given by the magnitude of the derivative of the unit tangent vector divided by, or the magnitude of the derivative of the unit tangent vector with respect to its arc length. And this is going to be where t is the unit tangent vector. Okay, so again, we got this in mind, and again, what I'm identifying here is that we have this Greek letter for curvature. This is kappa. All right, so it's a Greek letter kappa. And again, this curvature lets us know how quickly the curve changes with respect to its arc length. All right, so again, if we had some curve, and I'm going to draw this on the right-hand side, if we had some curve, and if we were to find this unit tangent vector, at any given point in time on this curve, then taking a unit tangent vector and dividing it, or in this case, taking the derivative of that, calculating how fast that unit tangent vector is changing with respect to the arc length. So now we see from unit tangent vector 1 to unit tangent vector 2 to unit tangent vector 3 to unit tangent vector 4, we're then going to be able to identify what was that piece of length for that arc from unit tangent vector 1 to unit tangent vector 2, and was there a lot of change? If there wasn't a lot of change there, then the curve doesn't have that big of a curvature. But look at the change on this unit tangent vector from T3 to T4. That direction then was almost a drastic change, right? And then from T3 to T5, we then have a bigger change there, which means there was some big curve that took place here. And it did. It practically switched directions, because from starting at the bottom from T1, this vector was pointing to the left-hand side of the screen, whereas moving over to vector T5 or T6, we're going to see that those unit vectors are now pointing towards the right-hand side of the screen, which means this curve did almost a 180-degree turn, and it's really just pointing almost in the opposite direction, which means there is high curvature at some point in time for that curve. And how are we going to calculate this? Well, we're going to calculate this by finding that change in the unit tangent vectors per their arc length. So how do we then go about this? Because finding kappa this way seems kind of daunting, because then we would need to find, well, what is going to be the arc length function and that whole process, and it could get rather, let's say, difficult. However, if we streamline this process, let's streamline this a little bit more. Okay, so here I have the derivative of the unit tangent vector with respect to its arc length. Okay, so that looks pretty good. Now, what if instead, whoops, let's go here. What if instead I did this, the derivative of the unit tangent vector with respect to time, divided by the derivative of the arc length with respect to time. Now, if I did this particular piece here, then that's going to be pretty good, because again, looking at my overall vector that we had on the left-hand side, that's going to leave me with some vector function that I'm going to take a magnitude, so then I'm going to be left with a scalar. In this particular case, I still get the exact same process if I take the magnitude of that numerator and divide it by the magnitude of that denominator. And in this particular instance, we're now left with something really, really nice. What's nice about this is that my numerator here, magnitude of the derivative of the unit tangent vector divided by time, well, that's going to just be the magnitude of t prime. Okay, so that's pretty good. Well, what about the denominator? Well, the denominator, that one looks oddly familiar. If you come back over here, that kind of looks oddly familiar, which means we're just left with the magnitude of r prime of t. As such. And so we've now gone from this whole process of finding this curvature just in terms of what we wanted to analyze, just again by wording what we want to see, to now having this mathematical definition for curvature. And curvature can actually be expressed in a different way as well. So we do have curvature being expressed as this value. So I'm going to express that down here. So we do have that curvature can be expressed as the derivative, the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position vector. So that's one option. The other option is to take the magnitude of r prime and cross that with r double prime, then take the magnitude, divide that by magnitude of r prime cubed. So we do have these two different options, and depending on what is given to us and what is being asked of us, we might prefer one curvature formula over the other. This is not to say that one is better than the other. It just means that depending on a scenario, we might want to use one over the other. All right. I've used both in different instances. So again, it's not one is not better than the other. So let's look at this example here when we're trying to look at curvature. So determine the curvature for the function r of t, which is going to be given by t 3 sine t and 3 cosine t. Now, my suggestion for you all is that we want to do this without finding the unit tangent vector. So what I want to do then is I want to go through and I want to use a cross product to see what we're going to be left with. Now, we could actually do it both ways, and you know, in the interest of time, since again I'm making these videos ahead of time, I'll go ahead and I'll work it out both ways. That way we can see that either way that you do this, you're still going to wind up with the exact same answer. So in order to use the second formula, that's going to be this formula that I'm going to be working with, that curvature is going to be equal to the magnitude of r prime, the cross product of r prime of t and r double prime of t, taking that magnitude, divided by the magnitude of r prime of t cubed. In order to work this out, I need my first derivative. So the first derivative here, we're going to get 1, 3 cosine of t, and then negative 3 sine t. Okay, great. Second derivative, r double prime, 0, negative 3 sine t, and negative 3 cosine t. Taking the magnitude, or sorry, taking the cross product, So taking the cross product, that's 1, 3 cosine of t, negative 3 sine t, 0, negative 3 sine t, and negative 3 cosine t. All right, so taking this cross product in the I component, we're going to have 3 cosine t multiplied by negative 3 cosine t. That's going to be negative 9 cosine squared t, minus minus, and then subtract another one, so that's going to be another minus, so that's going to be minus 9 sine squared t, which means we're left with 9 cosine squared t plus 9 sine squared t in the I component, minus the j component. The j component is just going to be negative 3 cosine of t, because the other components will cancel, plus the k component, which will be negative 3 sine t. The I component here will then simplify to just be 9. The second component, the y component, turns out to be 3 cosine of t. And then the last component turns out to be negative 3 sine of t. All right, so that's looking pretty good so far. Once we have this, then we can go ahead and we can take the magnitude. So taking the magnitude here, all right, this is going to be 9 squared plus 3 squared cosine squared t plus 3 squared cosine squared t, or sorry, sine squared t. All right, looking pretty good. Let's keep going. So now we have 9 squared, which is going to be 81 plus 9 here. There we go. So we get the square root of 90, which means finding the curvature here. Let me scroll down just a little bit more. Finding the curvature here is going to be the magnitude of the cross product, which we just found, which is the square root of 90, all divided by the magnitude of r prime of t cubed. So the magnitude of r prime of t, well, let's work on that really quick, the magnitude of r prime. So working on the magnitude of r prime of t, and we can do this one pretty fairly quickly. 3 squared, that's going to be 9 squared. Factor that out, plus 1, sorry, 3 squared plus 1, that's going to be 10, so that's going to be root 10. So this is going to be root 10 to the power of 3. Okay, that's not too bad. Square root of 90, that's actually 3 root 10, which means, check this out, this now simplifies to get us 3 divided by, and let me see what I have here. All right, 10, 10, and there we go. Yeah, 3 over 10. So the square root of 10's cancel out, and then in the denominator you have square root of 10 squared, which means you're just left with 10. So curvature here turns out just to be 3 over 10. Okay, that's kind of nice. Curvature in this particular case was constant. It's not always going to be the case that curvature is constant. Okay, curvature was 3 over root 10. Typically, you're going to get curvature as a function of t, which means you're going to be able to identify at what values you're going to have higher curvature than others. So once we have this, let's go ahead and let's start working with the next example. Or sorry, working with the next formula. The next formula for curvature is going to be the magnitude of t, and that's a unit tangent vector divided by the magnitude of the derivative of the position function. Okay, so again, we know r prime of t. This was given on the left-hand side of the screen. That's 1, 3 cosine of t, negative 3 sine t. Okay, well, we want the unit tangent vector, and the unit tangent vector is going to be r prime of t divided by its magnitude. So r prime of t, we have this as our vector, and then we're going to divide by the magnitude, which was as we found before, root 10. And now we don't want to leave this in this form, so what I'm going to do is I'm actually going to distribute that factor in. So let's distribute that factor in. Or you know what, I'll actually leave the factor out. I'm going to leave the factor out as 1 over root 10 is going to multiply the vector 1, 3 cosine of t, and then negative 3 sine t as such. Perfect. Because now I can take a derivative here because I want to take that derivative. So taking the derivative now, t prime, again the constant scalar stays on the outside. Derivative of 1 is 0. Derivative of 3 cosine t is going to be negative 3 sine t. Derivative of negative 3 sine t is going to be negative 3 cosine t. Good. Take the magnitude here. So the magnitude of this vector here, well, that's actually going to be nice. I can factor out a 3 as well. And so if I factor out a 3, then I'm going to be left with 3 over root 10 when I'm looking at the magnitude here. And then I'm going to be looking at the magnitude of this vector 0. You know what? If we factor out a negative, it turns out nice. Sine t and cosine t as such. And finding this magnitude of that vector is just 1, which means the absolute value of negative 3 over root 10 is just 3 over root 10 multiplied by that magnitude of 1, which just leaves us this. Awesome. So curvature now takes 3 over root 10, so 3 over root 10, divided by the magnitude of r prime of t. But remember, we found the magnitude of r prime of t on the left-hand side, and that was just root 10, which means 3 divided by root 10 divided by root 10 is just 3 over 10. There we are. Same answer. Same answer, different ways that we did it. So again, we want to keep that in mind, that there are different ways to get this curvature, and one way is not preferred over another. It just, whichever one we feel like working with, that might get us those results at a faster time. So let's look at different items now. I will also be working with a normal vector. And so working with a normal vector, this is going to be my you know what, I will label it as normal vector. And I'm going to name it as a unit normal vector. And the reason it's going to be a unit normal vector is because this is going to be based off of the unit tangent vector, taking its derivative and then dividing by its magnitude. So that is my unit normal vector. I will also be working with a binormal vector. And a binormal vector, that's a vector that is normal to two vectors. So this is a binormal vector, which coincidentally is also a unit vector, which you might have to prove on an exam. And this binormal vector is going to be denoted by b of t, and this is going to be made of the components for the unit tangent vector crossed with the normal vector. So again, we have the unit tangent vector that we work with, the unit normal vector, and the unit binormal vector. We work with those three different vectors. All right, so again, we have the unit normal vector, the unit tangent vector, and the unit binormal vector. We will also be identifying that we can have a normal plane. That normal plane is going to be the plane that contains the binormal and the normal vector. So if we ask for the equation of a normal plane, then the equation of the normal plane is the equation that contains binormal and normal vectors at the given point that will be given to us, and the normal vector to that normal plane will be the unit tangent vector. In other words, we're going to extract the components from that unit tangent vector, and those are going to be the components for that normal plane. Oscillating plane is another plane that we work with. That oscillating plane will then contain the planes, will then contain the vectors t and n. In other words, the unit tangent and the unit normal vector. And in this particular case, if we want to find the equation of the osculating plane, we just need to know what is a point P and then what is the normal vector to the osculating plane, which in this case it's going to be the binormal vector. Take the components from the binormal vector, insert those into the equation of the plane, and you then have your oscillating plane. And then lastly, we have a rectifying plane. This rectifying plane is going to be the plane that contains your unit tangent vector and your binormal vector, which means the other vector, which is the unit normal vector, is going to be the one that is normal to this rectifying plane. So if we wanted to find the equation of that rectifying plane, then all we need to know is what is the point P, because that's going to be on the plane, and then we need to know the components for this unit normal vector. Take those components, and you got your equation for the rectifying plane. So again, we do have different planes that we get to talk about when we're talking about this TNB frame. And this is exactly what this is. This is known as your TNB frame. Oops, excuse me. And the TNB, again, because it's made of the unit tangent, unit normal, unit binormal vectors, and they make a sort of frame for this object that's going to be traveling along this curve. So what we want to do right now is we want to work on this example that's going to say that we want to find the unit tangent, the unit normal, and the unit binormal for the vector r of t, which is given by cosine of 2t, sine of 2t, and 3. So starting off, finding the unit tangent vector, we need the derivative of r of t. Finding that derivative will be negative 2 sine of 2t. Finding the derivative for for sine of 2t will then be 2 cosine of 2t, and the derivative of 3 will just be 0. Finding the magnitude here, square the components, which should just be square root of 4, which is going to be 2. Therefore, my unit tangent vector will be negative 2 sine 2t, 2 cosine 2t, 0, all divided by 2. And again, we don't want to leave this in this form, so we simplify by distributing the scalar of 2, and we get negative sine of 2t, cosine of 2t, and 0. This is our unit tangent vector. So unit normal vector, what we'll have to do is we'll have to take the derivative of the unit tangent vector, and taking that derivative, we're going to be left with negative 2 cosine of 2t. Taking the derivative here for the second component will be negative 2 sine of 2t, 0. Finding the magnitude here, magnitude of t prime of t. Again, that magnitude is going to be nice. It's just going to be 2, and therefore my unit normal vector. The unit normal vector is going to be, again, the unit tangent, which is negative 2 cosine 2t, negative 2 sine 2t, 0, all divided by 2, which means this simplifies to negative cosine of 2t, negative sine of 2t, and 0. And then finally, we just need the binormal vector. Well, the binormal vector is going to be made up of the cross product of these two vectors. And again, when we find the cross product, we just do the I, J, and the K components. Okay, so let's see, unit tangent, that's then I'm going to factor out a 2 there, so let's go ahead and factor out a 2 from there. Let's see, what else can I do? Okay, so let me walk you through my thought process. Okay, so actually I can't factor out a 2. My apologies. So taking the unit tangent vector is negative sine 2t, then cosine 2t, then 0. And then taking my unit normal will be negative cosine 2t, negative sine 2t, 0. Which means we're going to be left with the I component. The I component is then going to just be 0. Minus the j component. The j component, again, 0. And then we're finally left with the k component. And the k component will be made up of sine squared 2t plus cosine squared 2t. Wow, that's kind of really nice. Which means that my binormal vector is just going to be 0, 0, 1. Nice. So let's summarize all of this. That way we can make sure that we've analyzed everything that we needed to. Unit tangent, that was negative sine 2t, cosine 2t, and 0. Unit normal, this was negative cosine 2t, negative sine 2t, 0. And the binormal vector, this one was 0, 0, 1. And there we are. We have all the components for that TMB frame. And again, if we wanted to frame this out, then we would just find the oscillating plane, the rectifying plane, and that normal plane that we were identifying, and therefore we'd be able to construct this TNB frame that we would be looking at for some object traveling on some curve. So I thank you all for joining me on this lesson, and I hope that you all enjoyed this lesson. And if you stick around, we will be talking about motions in space for the next lesson. So I hope to see you all then.